The ball is one of the most important teammates in tennis. The Penn tennis ball is certainly a tremendous performer. To ensure maximum levels of control, spin, durability, and speed, Penn balls are the result of a very detailed and specialized development and production process.
Many tennis players believe tennis balls are simply a commodity product. I can tell you, you'd be really surprised at the engineering skills required to produce such a high-quality tennis ball. We produce over 100 million of tennis balls in the world's most optimized tennis ball factory. Let's now take a look at the production together.
Penn uses a special blend of premium natural and synthetic rubber. Natural rubber alone would bounce, but not very high, and so 13 substances are added, which also gives the ball a longer life. From this special compound, pellets are then formed, calibrated precisely to the gram. At high pressure and a temperature of up to 320 degrees Fahrenheit, half shells are shaped. Afterward, the half shells are punched out. Now the half shells are abraded to an exact height and buffed. The buffed half shells are then edge cemented with heat-activated adhesive. Now, at high temperature, compressed air is injected into the ball core to ensure proper bounce, while the two shells are glued together. The balls are now bathed in a special glue, the last step before bonding with the felt. The felt is very important for more spin, more control, and more durability. Special high-density premium felt consisting of a blend of New Zealand sheep's wool and nylon. Dog bone-shaped pieces are cut out of the felt. These dog bones are bundled and heavily compressed. In the dipping bath, the edges of the dog bones are treated with a white glue, a latex solution. This creates the typical white seams you see on a tennis ball. The felt is wrapped onto the core with ultimate precision in this machine. Invented by Penn engineers, it's the only one of its kind in the world. For the first time, the result looks like a tennis ball, but it's not finished yet. The rubber core and the felt are finally indestructibly bonded by applying heat and pressure. Afterward, the balls are filled into this special steam machine, which prepares the felt for ideal playing characteristics. Now the logos are printed onto the balls. Penn also produces its own cans and labels. Packaging of the balls is automated. The cans are pressurized to ensure that the balls retain their internal pressure and stay fresh until the can is opened.
These are the three things that people really want. Most people don't want to be really wealthy. What they do want is they don't want to have any financial concerns. If they want to buy a new suit, they can go and get one. If they want to take a trip, they can take the trip. They don't want to just run out and spend or buy. They don't want to have any financial concerns. Two, they want to wake up in the morning excited about how they're going to spend their day. And the third, they want to mix with people who are upbeat and creatively productive.
Remember this, guys, you cannot hang out with negative people and expect to live a positive life. Find the best people, work with them, make an effort to make them your friends. Great suggestion, how to get the wrong people out of your life. I don't get mad, I disappear. I've seen people in big fights and arguments. Don't fight. You can't affect people who don't see a problem in their own actions, so just disappear.
I'm Jake O'Neill, creator of Animographs, and this is how solar power works. Let's start in the heart of a single solar cell. Particles of light, which we call photons, enter the solar cell and are absorbed by available electrons, exciting the electrons to a higher energy level. Excited electrons travel out of the cell and through an external circuit where they exchange this newly gained energy to do work. The spent electrons return to the cell, ready to absorb more photons. The supply of extra electrons, and the force that turns a solar cell into a sort of electron pump or motor, comes from joining two special types of silicon material together to generate a reaction where they meet. This is called a p-n junction. Making a p-n junction. Electrons in the outer shell are used for bonding with other atoms. Stable atoms generally favor 8 electrons in the outer shell. So silicon atoms share electrons when bonding to meet that number. We need extra electrons to do work. It's possible to add small amounts of impurities to silicon that change its molecular structure. This is called doping. P-type silicon, P for positive, is doped with boron, which has 3 electrons in its outer shell, leaving an extra open space or hole when bonding with silicon. When an electron leaves an open spot, other electrons naturally fill it in sequence. For our purposes, it's convenient to track the open space or hole as it moves. The space charge region. The space charge region forms at the junction where P and N-type silicon meet. When these doped silicon types are layered, unequal electrons and available spaces, or holes, naturally seek to recombine across the junction, attempting to equalize. Electrons just naturally move around a lot easier than protons. When these electrons wiggle free and try to equalize, the imbalance creates special, electrically charged atoms with unequal electrons to protons, called ions. These opposing positively and negatively charged ions eventually prevent further electron and hole diffusion. An electrical field exists in the space charge region. Excited electrons are attracted and swept in the positive direction, and holes in the negative direction. As such, electrons can't go backwards, and must travel an external circuit to recombine with an open space, instead of simply doing so inside of the cell and wasting their newly gained photon energy as heat. Supporting structures. Let's look at other parts of the solar cell that support the core process. Anti-reflective material. Polished silicon alone wastes a lot of light by reflection, so anti-reflective coating is added for improved efficiency. There are many types of anti-reflective material. In this example, a grid of microscopic inverted pyramids directs and captures light at many different angles, giving it maximum opportunity to enter the cell and remain longer inside. Photons can be absorbed at any point throughout the cell. Front contact. Metallic fingers are screen printed and bonded to the top of the cell. They're designed for optimal charge collection, but minimal shading. Aluminum rear contact. A rear aluminum layer completes the electrical circuit. Electrical contacts protrude through the passivation layer. Glass top layer. A thick layer of low iron glass protects the cell from outside conditions and provides structural strength while also allowing maximum light passage. Low iron reduces the reflective impurities that give normal glass a faint greenish blue tint.